Hello everyone, this is Professor Roman. Welcome to the 20th video in my video series, An Introduction to Discrete Mathematics. In this video, we will continue our discussion of counting techniques, of combinatorics, and we're going to begin this study officially in this and the next section with two very simple yet very powerful rules. In fact, much of what we're going to do even after this section and the next is going to depend on these two basic counting principles. So it's very important that you have a good grasp on these two techniques before moving on. Now it happens that many counting problems amount to counting the number of ways to perform a certain sequence of tasks. By sequence, I mean you perform the first task, then the second, then the third, and so on. And each task can be performed in a certain number of ways, and you know how many ways each task can be performed. What you're looking for is the number of ways that the entire sequence of tasks can be performed. As a simple example of this task business, remember the first example that we talked about in the last video, counting California license plates. Constructing a license plate amounts to performing 6 tasks. The first task is to choose the first letter. The second task would be to choose the second letter. Third task, choose the third letter. Fourth task, choose the first digit, and so on. Okay. Now, each of the first 3 tasks, the letters, can be performed in 26 different ways. Each of the other 3 tasks can be performed in 10 ways. So this is the ideal setup for the multiplication rule we're going to talk about next. A sequence of tasks, and you know how many ways each task can be performed. But there's one hitch that's extremely important. The multiplication rule applies only to the situation where the tasks to be performed enjoy a certain independence, in the sense that the number of ways to perform any given task does not depend on how the previous tasks were performed. This is critical. If this independence condition is not satisfied, the multiplication rule will give you the wrong answer. And to be absolutely clear, the ways to perform a given task may depend on how earlier tasks were performed, but the number of ways to perform that task must not depend on how the previous tasks were performed. If that seems a little confusing, when we do some examples, it should clarify. Here is the multiplication rule in all its glory. Suppose that T1, T2 up to Tk is a sequence of tasks with the property that the number of ways of performing each task does not depend on how the previous tasks were performed. In other words, the outcomes of the previous task. If there are n sub I ways to perform task T sub I ranges from 1 to k, then the total number of ways of performing the entire sequence of tasks is the product, n1 times n2 up to nk. This is called the multiplication rule because you multiply. It's also called the fundamental counting principle, which should give you a hint that this is, well, fundamental. It's very important. Let's look at the first example. This again is the license plate problem. We've already discussed there are 6 tasks. They do enjoy the required independence. The number of ways, for example, to pick the second letter does not depend on how the first letter was chosen. And that's because you can use the same letter more than once. Okay. And similarly for the other tasks, they have this independence that's required. And so we multiply 26 times 26 times 26 times 10 times 10 times 10. 17,576,000 California license plates. Now, in my experience, some students get a little confused between multiplying these numbers together and adding them. They want to add sometimes. But you must multiply. And the easiest way to see that and to remember is to do a very simple 2-task sequence. Suppose you want to choose a single letter followed by a single digit. Well, for each of the 26 letters, there are 10 choices for the digit. So to get the total number of ways to do both, you're going to add 10 to itself 26 times. That's 26 times 10. That's why you multiply. If the problem were to count the number of ways to perform either task, exactly one task, either choose a letter or choose a number, now you add. You get 36. The multiplication rule is really quite simple, but it is amazingly powerful. And you'll see that as we work through various counting problems. The catch, of course, in using this rule is really twofold. First, you have to figure out what the tasks should be for a given problem. If it's a simple problem like the license plate problem, it's pretty obvious. What I like to tell students is, imagine you're in jail and the warden says, you're going to make license plates. What are you going to do? Well, you're going to stamp out the first letter, then you're going to stamp out the second letter. You do have to do it by hand. Then you're going to stamp out the third letter, then you're going to stamp out the first digit, second digit, third digit. You're going to perform these 6 tasks, literally. How many ways can you do it? Well, you got 26 choices for the first letter, times 26 for the second letter, times 26, and so on. When the problems get more complicated, it may not be so easy to break the situation up into tasks. It may not be so easy to choose the appropriate tasks and the order in which you perform the tasks. And we'll see an example of that in a minute. Okay. Keep in mind, too, that the independence condition is critical, and you must always check it. Do not forget to check that. Also, there's often more than one way to define the tasks and solve the problem. So that's something to consider as well. Here is a simple example. The multiplication rule can be used to count the number of words of a certain length over a certain alphabet. So to determine the number of words of length n over an alphabet of size m, how do you do that? How do you construct a word? You choose the first character or letter in the word, and since the alphabet has size m, there are m choices. Then you choose the second letter, also m choices, and so on. This is a lot like the license plate problem. If the license plates were all the same, all letters, all digits, whatever. So you just multiply m by itself n times because the words have length n. So it's m to the nth power. That is the size of sigma sub n when the alphabet has size m. For binary words, for example, m is 2. You only have 0 and 1 in the alphabet, so there are 2 to the n binary words of length n. You can use what we've just done to compute the size of gamma sub n, which, if you recall, is the number of words of length at most n. Okay. And I'm going to skip over this. It's not very long because I think it would be good practice for you to do. Okay. Here's an example of a totally different nature. Question: how many even integers with distinct digits are there between 1 and 99? You may not find this to be a very pressing question, but it's a good example of the use of the multiplication rule. First of all, it's a little disturbing that some of those digits only have one character, and most of them have 2, and that's awkward. But we can deal with that very easily just by putting a 0 in front of the single digit numbers. So 0, 1, 0, 2, up to 0, 9. And now we can think of all of these integers as having 2 digits. Well, there are 2 ways now we could proceed. It sounds like a 2-task problem, but which task should come first? Well, you might think, well, the first task should be the choice of the left-hand digit from among the 10 possibilities, 0 through 9. The second task would then be to choose the right-hand digit. It is from among the even numbers because the 2-digit number has to be even, so we can choose 0, 2, 4, 6, or 8. But when you check the independence condition, you run into trouble. The way in which we perform the first task, the choice of the left-hand digit, affects the number of choices for the second task. If we choose an odd digit for the left-hand position, we're free to choose any of the 5 even digits on the right. But if we choose an even digit on the left, we can't choose that again for the right side, so we only have 4 choices. So the number of choices for the second task depends on how the first task was performed. So this procedure fails the independence condition, and you can't use the multiplication rule. And I would urge you strongly, if that went a little too fast, to stop the video, read it again until you see clearly that this is a problem. The other choice would be to reverse the tasks. The first task would be to choose the right-hand digit from among the 5 possibilities, the even numbers. The second task is to choose the left-hand digit from among 0 through 9. But we cannot choose the digit for the left hand that we've already chosen for the right hand. That's okay. That does not violate the independence. Once we choose the right-hand digit, there are 9 choices for the left-hand digit, not 10, because we can't choose the same digit again. But there are always 9 choices. It doesn't matter whether you choose the right-hand digit to be 0, 2, 4, 6, or 8. Whatever you choose, that one integer is eliminated from your possibilities for the left-hand digit. So that's 9. Now the multiplication rule tells us that we have 5 choices for task 1 and 9 choices for task 2, and so we get the product 45 even integers with distinct digits between 1 and 99. Now I want to be absolutely clear here because this is such a critical point. I apologize if you've already got it and this is belaboring a bit, but it is true that the actual choices for the second task depend on how the choice of the first task is done. But the number of choices does not depend, and that's the critical independence. Also, it's worth noting that the first attempt, while it's going to fail, is not without some merit. We can make it work, but we have to divide the problem into 2 parts. If we choose, so we're going to choose, the first task will be for the left-hand digit. If we choose any of the 5 odd digits for the left-hand position, we can choose any of the 5 even digits for the right-hand position. Okay, so the multiplication rule tells us that there are 5 times 5 or 25 even integers between 1 and 99 with distinct digits whose leading digit is odd. If, on the other hand, we choose for the one of the even integers for the left-hand position, we can't choose that anymore for the right-hand position, so the number of choices drops to 4. So it's 5 times 4, which is 20. These 2 options are mutually exclusive. They're disjoint. Choose even or choose odd for the left digit. So we add those 2 numbers, 25 and 20, and we get 45, just like we did before. So it's more work, but it still will work. But you must not jump to the conclusion. If you ignore the independence condition, you'll get the wrong answer. So the moral here too is you should think about the order of the tasks. If the order you've chosen isn't working out, try a different order. That may work. Okay. The multiplication rule can be used to determine the number of subsets of a set of size n. We've already done that using mathematical induction. We know that a set of size n has 2 to the n subsets. The problem with proof by induction is that we already needed to guess the answer. Induction doesn't give us an answer. It proves that our conjecture is true or not. So we need the conjecture first. But if we use the multiplication rule, we don't need to make any guesses. Suppose that we have a set little s1 through little sn of size n. Think about this construction business like the license plates when you're in jail. How do you construct a subset? Well, you can do it by performing a sequence of n tasks. The first task is to decide whether or not the first element S1 belongs to the subset. The second task is to decide whether or not the second element S2 belongs to the subset, and so on. Each task can be performed in only one of 2 ways. Yes or no, include the element, don't include it. These tasks have the required independence. The number of ways to say yes or no on any given element doesn't depend on what's happened before. You've always got 2 ways. So Multiplication rule says multiply 2 together with n factors, 2 to the n. Okay, let's move on to the next counting principle. It is called the pigeonhole principle. Officially, it's the Dirichlet pigeonhole principle because it was named after the French mathematician Peter Gustave Lejeune Dirichlet, but everybody calls it the pigeonhole principle. And this one is very simple, even simpler than the multiplication rule. If m balls are placed into n boxes, and if m is bigger than n, then at least one box must receive more than one ball. And this seems pretty obvious. If you had 6 balls and you had to put them in the 5 boxes, clearly some box must get at least 2 balls. And I guess it's kind of surprising that such an obvious rule can be very useful at times. But we're going to look at some examples now. What is the largest number of points that can be placed in a square whose side has length 2 in such a way that the distance between each pair of points is greater than the square root of 2? Well, here is a square whose side length is 2, and I've divided it into 4 equal squares, side length 1. According to the Pythagorean theorem, then, the diagonals of these little squares have length square root of 2. Therefore, we cannot place 2 points within the same square. In other words, we can place at most 1 point in each square. If we said that's 4 points. Okay. If we had 5 points and 4 squares, the pigeonhole principle would tell us one of the squares will have to get at least 2 points. So what we know now is that we can place at most 4 points in this large square. But certainly we could put the 4 points at the corners of the large square, and they would be at least 2 units apart. So that would solve the problem. So the answer is 4 points. The pigeonhole principle can be used to solve some problems from a branch of mathematics known as number theory, which you could describe rather simplistically as the study of the integers. Number theory is a very deep field of mathematics with many unsolved problems. Here's a first example. Given any subset S of n plus 1 integers from the set of integers from 1 to 2n, there must be 2 integers from the subset with the property that one of them divides the other one. So for example, if you have 6 numbers from among the numbers 1 through 10, one of those 6 numbers must divide another one of the 6 numbers. Now, the key to solving this problem is to write the integers in the subset, in fact, any integer, as a power of 2 times an odd number. You can always do that. 84 is 2 squared times 21. 26 is 2 to the first times 13. 7 is 2 to the 0 times 7. Now the odd factors in such a factorization, since that we're dealing with the numbers between 1 and 2n, the odd factors have to be between 1 and 2n minus 1. 2n is not odd. We could be a lot more restrictive, but this is good enough. There are only n odd numbers in this range from 1 to 2n minus 1. And I'll let you think on that. You have the tools to prove that. So the pigeonhole principle tells us that at least 2 of the integers in the subset have to have the same odd factor. Okay. There are only n odd factors, but there are n plus 1 numbers. So there are n plus 1 odd factors. There are only n odd factors in the range here, but there are n plus 1 odd factors in the subset. Okay. So 2 of the elements in the subset have the same odd factor. So we'll call them A and B. A is 2 to the I times m, and B is 2 to the j times m, where m is odd. Well, either I is less than j or j is less than I. If I is less than j, then A divides B. And similarly, j is less than I, then B divides A. This is a problem that you might spin your wheels on for some time unless you think of this key idea of writing factoring the integers in this way. And then the pigeonhole principle becomes relatively apparent and you can solve the problem. So I'm not saying this is an easy problem. It takes an idea. Okay. Let's look at this one. Given a collection a1 through an of n integers, not necessarily distinct, there is some subcollection of these integers whose sum is divisible by n. So this also requires an idea, some thought, and that is to consider the running sums. S1 is A1, S2 is A1 plus A2, S3 is A1 plus A1 plus A3, A1 plus A2 plus A3, and so on. Now we divide each sum, Si, by n, and write the quotient at the remainder, as elementary school kids would do, I suppose. The remainders, upon division by n, lie between 0 and n minus 1. There are n possible remainders. Well, it kind of looks like we're stuck, at least with respect to the pigeonhole principle, because there are n sums and n remainders. But here is the thing. If any one of the remainders is 0, say R1 was 0, for example, then S1 would be Qn, and so that's divisible by n. The only other possibility is none of the remainders are equal to 0. But then there are only n minus 1 remainders possible. But we have n remainders R1 through Rn, so 2 of the remainders must be equal. Say that's Ri equal to Rj with I less than j. Then we take the difference, Sj minus Si. That is also a sum of the elements from the collection. And because both of the remainders are the same, when you divide this difference by n, the remainder is 0. In other words, this sum is divisible by n. That's a nice problem. And the pigeonhole principle is the key once you notice that you have to do a little tweaking. Okay, that's enough, I think, for this video. We've talked about the fundamental counting principle or multiplication rule. We talked about the pigeonhole principle, and we saw some more or less simplistic examples and some substantive ones, some very interesting ones. So thank you for watching, and I hope to see you in the next video.